Alright, in this lesson we're going to look at situations where we have objects that are in what we call free fall in physics. And free fall basically means that an object is falling under the influence of gravity. Now, one thing we probably know about gravity before we even started this course is that gravity applies a downward force on all objects. Downward as in toward the Earth. When objects are falling close to the surface of the Earth and air resistance is negligible for those objects, what happens is all objects experience the same acceleration due to gravity. And this acceleration is nearly constant for the object if the distance the object has fallen is small compared to the radius of the Earth. The radius of the Earth is something in the thousands of kilometers distant. So this would work for, dropping something off of a tower. It could work for skiing down a mountain. You could even be dropping an object from an airplane and still have the distance the object has fallen is small compared to the radius of the Earth. Magnitude of the acceleration is 9.8 meters per second squared. I usually will use the symbol g to talk about the acceleration due to gravity, and the acceleration when we add its direction is 9.8 meters per second squared down toward the surface of the Earth. Let's do a couple of sample problems. The first one deals with dropping a rock off a small building, and let's say the rock has fallen for 3 seconds. And I want to figure out what is the velocity of the rock when it hits the ground, and how far did the rock fall. Or I can actually use a very similar technique to what we used before in my kinematics problems. Read the problem, identify knowns and unknowns. Some things that I know: if I drop a rock off of a building, its initial velocity is 0 when I let go of it. The time it's fallen is 3 seconds, and because I know this is a free fall problem, I'm dropping it off a building, the acceleration is that due to gravity, negative 9.8 meters per second squared. Two unknowns are v and x. What is the velocity of the rock after it fell for 3 seconds, and what is the distance the rock traveled? If we look at the equations I would use to calculate v, I'd do v initial plus at. To calculate x, v initial t plus 1/2 at squared. Since v initial is 0 in both cases, that first term in both these equations cancels out. I get v is equal to at and x is equal to 1/2 at squared. And at this point I can substitute my values in. V is equal to negative 9.8 times 3. X is equal to 1/2 times negative 9.8 times 3 squared. And so what I get is that the velocity of the rock is negative 29.4 meters per second, and the rock has fallen 44.1 meters. What the negative signs really tell you in both of these is that it has gone, in terms of distance that the rock fell, it went downward. In terms of velocity, the rock was moving downward when it hit the ground. So let's test an urban myth. And urban myths or urban legends are kind of legends or myths that surround some sort of usually popular cultural figure or some sort of popular idea. This one surrounds the basketball player Michael Jordan. And the myth about Michael Jordan is that when he jumped, he could stay in the air for more than 2 seconds. Could there be some truth to this myth? We know that Michael Jordan, nicknamed Air Jordan, could supposedly stay in the air for a long time. You always see those pictures of him doing those massive dunks over somebody. But let's check out the truth to this myth. Now, if he's going to stay in the air for 2 seconds, he has to jump up and come back down during those 2 seconds. So let's call that distance x, how far he can get in the air if he jumps up. Well, if he's going to be in the air for 2 seconds, he's going to be jumping up for 2 seconds, jumping up for 1 second and falling for 1 second. If the acceleration due to gravity is constant, the amount of time it's going to take him to go from the ground to the highest point of his jump is equal to the amount of time it takes from the highest point back to the ground. Now, at the top, let's just assume he's jumping straight up in the air. The velocity at the top is 0. We can actually think about why that's true. As you're jumping upward, you have positive velocities, but they're getting smaller and smaller and smaller. As you're falling down, you have negative velocities, and they're getting more and more negative. So at the top, there must be a point where velocity is 0. So my objective is going to be find x and see, is this reasonable for somebody to do? So here's the data I'm going to use. I'm going to say, look at what happens in the fall part of this motion, the time being 1 second, the initial velocity being 0 meters per second, how fast he's moving up or down at the top of his motion, and the acceleration negative 9.8 meters per second squared. and we can apply this formula. V0t cancels out, and what you get is that in order for him to be in the air for 2 seconds, he'd have to have fallen 4.9 meters. So this would also mean that he would need to be able to jump 4.9 meters into the air. Now that's about 16 feet. For sake of reference, the basketball net is about 10 feet off the ground. In fact, 10 feet off the ground. And we're not talking about he's getting the ball 16 feet into the air. We're talking about his feet are 16 feet in the air. Maybe to give you a picture, imagine me standing on top of a basketball hoop. I'm a little under 6 feet tall. He would be able to jump over my head without lifting his legs up. So we can probably all agree that, hey, it's ridiculous for him to jump 16 feet in the air. So there's no way this myth could be true. Now you might be saying, wait a second. I see what you're saying right now, but obviously Michael Jordan never jumped straight up in the air. How often have you ever watched a basketball game and you see a basketball player dribble to underneath the net, stop, and then jump straight up in the air to try to dunk the basketball? It never happens. And there are reasons why it never happens in basketball, because, well, you lose a lot of your offensive advantage if you stop. So he's always running toward the basket and jumping, so does moving both horizontally and vertically at the same time make a difference? Does the fact that he's running at the basket while he jumps up in the air make a difference? Maybe he doesn't need to jump 16 feet into the air if he's running toward the basket at the same time. Now, one of the things I'm going to show you, and I'll put a link on the Moodle for, is this Mythbusters video where they do a shot bullet versus a dropped bullet. And so they're basically testing this same idea. Does horizontal motion impact vertical motion? If this is true, having horizontal motion should allow you to stay in the air longer. What they did was they took a bullet and shot it horizontally, and they shot it at the same time that they dropped a bullet vertically, and they wanted to check how long does it take for each of those bullets to hit the ground. I'll let you watch that Mythbusters video and figure out what the answers are. We'll actually also do a demo in class where we actually look at this idea and actually test, does this horizontal motion make a difference? Obviously, in most situations, at least in this one, there's not just vertical motion going on, there's also horizontal motion.